So now we really want to get to the nuts and bolts of what we were trying to do, which is approximating area. And I go into it in pretty great detail over here. Let me explain it in general first. And then we can look at those notes. And hopefully, having seen it twice, it makes more sense to you. So I had said that we're trying to approximate the area under this curve with the sum of rectangles, and that's what 4.1 is about. I had said that we're going to chop up our interval into n equal pieces. So in my picture, I have n equal to 6. And because each of these pieces are equal, that gives you the width of the rectangles. Then the next thing that we want to do is we want to formulate something called the Riemann sum. This Riemann sum is the sum of areas of rectangles and rectangles in general. So when I write this, you know you're adding together n things now. And all we need to put on the inside here is we need the area of the ith rectangle. Okay. So let me actually take this picture and bring it downstairs. Let's put it off to the side right here. So just so you can keep track with what's going on, what we did was we chopped it up 1, 2, 3, 4, chop it up into n equal pieces. We're calling the width of this piece right here delta x. And now I need to add up the bunch of rectangles. So I could have it look like this. Can come up here like this, come up here like this, come up here like this, come up here like this. And come up here like this. And at this point, we're kind of faced with a choice. I could, well, let me say one more thing before I go there. So what we're really working with over here is if we're looking at the sum of these n rectangles, then we just said that the height of a rectangle is given, the area of a rectangle is given by the height times the width. And we already found the width. The width is what we are calling delta x. So this is really, as I goes from 1 to n, we're going to have a delta x here. So the natural question to ask is, what is the height supposed to be? And the answer to that question is the height should really depend on the function. Now in this class, we're only going to look at 2 options for the height. The first option is we can choose the left endpoint. So if I chose the left endpoint, that would look like this. Do you see how at each interval, I go to the left side of the subinterval, and then I evaluate the height of the function. Same thing with the second guy. I go to the left of the subinterval, and then I evaluate the function to get the height. I do that for each one of these rectangles. That's the first option. The second option is you use the right endpoint. So for the first rectangle, I use the right endpoint. Second rectangle, I use the right endpoint. Third rectangle, I use the right endpoint. Fourth right, fifth right, and sixth right. So I hope you can see that for one of them, I got an area that was a little too small. This particular one is an overestimate, right? So we have like a little bit too much area. So the true area is like somewhere in between. Okay. But in general, I would say that the height is determined by the function evaluated at either the left or right endpoint. Okay. So when we don't want to specify, we're going to use xi star. If we don't want to specify. So I'm going to come over here and I'm going to erase this question mark over here. And this is going, I'm just going to write in here, this is f of xi star. And this is our Riemann sum, our most general Riemann sum. Okay. So, mathematicians, we like to express things in the most general form possible and then sort of specify later. So I can actually also break it down like this. I could say if we use the left endpoint or if we use the right endpoint, and I can show you the difference between those. So let me refer back to my worksheet. If you go to our worksheet over here, we have this we have our picture. When I chop it up, we actually call this a partition. So this collection of chopped up, I guess we call each of these things subintervals over here. That collection of subintervals is called a partition. And when I don't want to specify, when I want to talk about a general subinterval, I use xi minus 1 xi. So if I were to label that right here, if this was my sort of general subinterval, then this would be xi minus 1, and that would be xi. Okay. So, so when I use the left endpoint, we plug in a xi minus 1. And we call this L sub n. L because we're using the left endpoint, and n because we're doing n rectangles. For the right endpoint, that's going to be called R sub n. And that's very similar. We just add up n rectangles. Instead of plugging in xi minus 1, you plug in xi. You got delta x there. So these are the two ways that we approximate our integral. Okay. Any questions so far? I feel like I said a lot there. Do you have any questions? No questions. All right. Ian, you got any questions for me, or is this making sense? Who else sometimes asks questions? Nick, you have any questions for me, my friend? No. Okay. Cool. So, good. So this is basically what we're dealing with these Riemann sums. So this is basically repeating everything that I just said. The regular partition means the intervals are equally spaced. And this is the left endpoint approximation. and this is the right endpoint approximation. Okay.